This video is about emission spectra. This is a Chem 101 topic, and it also relates to the flame tests that you may have done or observed in lab. So atomic spectra in general, this is related to a couple of ideas, and that is when elements, so these are the substances on the periodic table, elements themselves, when they absorb energy, they emit light. And of course we can separate light into colors using like a prism. In class you would have used a spectroscope to look at light sources and separate it into its different colors or wavelengths. And when you take an element that's emitting light and you separate it into its colors, then we call that an atomic spectrum or an emission spectrum. And what's important, the whole point of this exercise, is that the emission spectrum we see from an atom, from an element, does not resemble the full spectrum of white light. Okay, so white light exhibits a full visible spectrum that looks like a rainbow. So this would be a continuous spectrum like you see here, from violet going into various shades of blue, into aqua, into green, all the way through to red. So this would be a continuous kind of spectrum. And this would be what you see if you separate white light into all of its different colors. So white light would be light that comes from the sun, for example, or from incandescent light bulb. Now atomic spectra don't appear like this, though. Atomic spectra appear in lines. And so this is an emission spectrum or an atomic spectrum. We also sometimes call this a line spectrum because all you see are very discrete lines of certain colors. A given element, for example, this is the atomic spectrum of hydrogen. It'll always look like this. If you're looking at a hydrogen source and it has energy that's being put into it, probably electricity from the wall, it will emit light. And if you separate that light into its different wavelengths using a spectroscope and you look through the spectroscope, you would see this line spectrum instead of the continuous spectrum you see above. And the purpose of this video is to explain why this is true. So if we move on, I wanted to clarify the idea of an incandescent light bulb. So white light sources would be, for example, the sun. If you look out the window using the spectroscope, of course it has to be daytime for you to do that, or if you look at an incandescent bulb, then these are definitely sources of white light and they would give you a continuous spectrum like you saw. However, not all light bulbs are incandescent bulbs. The bulbs in the room, or complex fluorescent lights, or the lights that are in the room that you're probably sitting in right now, these are fluorescent lights, and these are not sources of white light. These are actually elements inside that are being energized using electricity, from the building, and that energizes an element. They are usually mercury lights. And so when you look using a spectroscope like you see here, if you look at the white light sources, it would look like this through the spectroscope. But for example, the fluorescent lights in the room have mercury inside, and so that would look more like this, where this is a line spectrum instead of a full spectrum of white light. So the light bulbs you use, some are sources of white light and some are not. So this is a picture of the visible emission spectrum of hydrogen that we've already looked at a little bit, and you can see there are clearly 4 visible lines. There's a violet one, kind of a bluish one, sort of a teal colored line, and a red line. Now this is not the entire emission spectrum of hydrogen, this is just the visible region. Okay, so this is visible. If you remember, this is the sort of just the middle segment of the electromagnetic spectrum. You can see the visible region is just a small portion of that. Just to the left, just shorter wavelength of visible would be on the left on this figure. That would be ultraviolet light. And there are emission lines in the UV region for hydrogen. Those are called the Lyman series. It's named after the scientists who originally saw those. So that would be the UV region over here. There's also some lines in the infrared region called the Paschen series, and that would be over here. Here's a picture from a different textbook that shows what those look like. You can see those here. So the visible region is A. And you can also see now that sometimes there are actually 5 lines in the hydrogen spectrum. That 397 nanometer line, sometimes some people can see that and some people can't see that, and so that one's sort of optional. Sometimes you see it and sometimes you don't, so just depends on your eyeballs. But at the bottom you also see the other two, the Lyman and the Paschen series, in addition to the Balmer series, which is the visible spectrum. Now, I want to talk a little bit about why you see these line spectra. So let's start by talking about light absorption and light emission. Now, we've talked about absorption before when we did the Kool-Aid lab, and we observed sort of the absorption spectrum of the different Kool-Aid dyes. And then what we're looking at now are emission spectra, which are a little bit different. This is when the matter gives off light as opposed to absorbing light. And so the idea here is that light has energy. The energy is related to Planck's constant and the frequency. So the higher the frequency, the more energy it has. Light can be absorbed by matter, and then the matter will have higher energy. It'll be in an excited state, is what we say. And then, but excited states with higher energy are less stable, and they often fall back down to their lower energy state. And then they would emit light, and so light can also be emitted by matter, and if the matter emits light, it will have a lower energy than it did in the beginning. And so light has energy associated with it. And I want to talk about the absorption and emission of light. So let's look at this here. So this would be an electron. That's shown by that red arrow. That's an electron. And here it's in an orbital at the bottom, the lowest energy orbital possible. And this is hydrogen. It has 1 electron. If we shine light on it, and the sample, if it absorbs that light, then it's going to promote that electron to a higher energy state. And we would call that the excited state. The lowest energy state is called the ground state. You see that on the left. The ground state is the most stable state. That's where it wants to be. But if you shine light of a certain wavelength on it, it will absorb that light and it will go to an excited state. Now here I put it in the 2nd orbital. It could be in the 3rd orbital or the 4th orbital. It just depends on how much light it absorbs. If it absorbs sufficient light to move up to the next orbital, it will do that. But this excited state is unstable, and so it will later fall back down to the ground state. And this is certainly going to happen. Now when this happens, this is when light would be emitted. Okay, so light is absorbed and it gets promoted from a ground state to an excited state, which is unstable and will fall back to the ground state. And when it does that, it emits light at the same time. So when you see emission spectra, what you're seeing is the matter going back to the ground state and giving off light. Now where does it get that energy from, right? It absorbed energy. And the energy typically, if you're using like the fluorescent light bulbs on the ceiling, the reason from the ground state to the excited state is because we put electricity into it, and that gave it energy, and that caused it to get promoted to a higher energy state. But because it's unstable, it then falls back to the ground state, and that's why it gives off light. Okay, now let's move on. So the line spectra of hydrogen caused Niels Bohr to introduce his idea, his model, called the Bohr model now, of the atom. Now we know now that this model has some true aspects to it and some not true aspects to it, but we're going to talk about the model because it's really important. So Niels Bohr developed a quantum model of the hydrogen atom, and that is true. That is definitely something that is true about the hydrogen atom. It's based on the emission spectrum of hydrogen, which is shown here. So you see the 4 lines. And so the emitted light that Niels Bohr observed was not white light. It did not represent all wavelengths. It only represented 4 very discrete wavelengths, very discrete colors that you see here. So that means that the energy that's being emitted is only 4 very discrete values, not all the possible values that could be observed. So only a few wavelengths were observed. And so that caused Bohr to create this model of the atom, where he stated that electrons, that was the arrow, remember they got promoted to the next level, electrons travel in what he called orbits around the nucleus at very specific distances, and that those have specific energies associated with them. And you can see the arrows here. The arrows are meant to indicate when an electron falls from one orbit to a lower orbit, lower energy orbit. That's what causes, remember, the energy to be light to be emitted. So here, this Bohr model, these orbits that we just looked at are on the left, and now we have a sort of more detailed visual of this on the right, and you can see different size arrows here, right? So there's 1, 2, 3, 4, 5 different sort of purple colored big arrows. Okay, those are meant to represent the lines in the ultraviolet region of the spectrum. That's the Lyman series. The Balmer series, the visible region, those 4 visible lines are shown with the green arrows in the middle. They're different size arrows, as you see. And then the infrared region, the Paschen series, those are the 3 smaller red arrows on the right. And so you can see the size of the arrows indicates the amount of energy that's going to be released. And that's related to the frequency, right? So ultraviolet light has the big giant arrows. Those have high energy and high frequency, which ultraviolet light does. And then the infrared, the red lines, those red arrows are very small in comparison, and those are going to have lower energy than visible light, and it has lower wavelength, lower frequency, longer wavelength, right? And then the visible Balmer series is in the middle. So now we have white light on the top and the emission of hydrogen. Now the bohrium, we named element 107 after Niels Bohr in honor of his contribution, the Bohr model of the atom. These are emission spectra of different elements. Hydrogen we've already looked at the top, followed by helium and neon. Mercury, the lights in the room that you're in right now are probably have mercury in them, and they probably resemble this fourth series. Oh my God, I need to turn off my phone. These people are killing me. Sodium at the bottom is an interesting spectrum, and it just has the 2 yellow lines in the middle. And so if you've ever heard of sodium lights, those are sort of the yellow looking lights that you sometimes see that are used as street lights in certain parts of the country. And this also relates to, now remember there are going to be other lines in other parts of the spectrum. This is just the visible region. This also relates to the flame tests that you've done. So sodium is one of the common flame tests that we do. These other ones we don't usually do. But sodium is examples, and so the sodium would be the flame test in the middle here. The one on the right, I can't tell. I guess that's kind of purpley colored. Remember, potassium is kind of a purple color. The one on the left is, it might be calcium. I'm not really sure. So different flame tests for different elements are related to the emission spectra. And so in this case, the energy going in is from the flame, and then the color that you see is energy that's being emitted as it falls back to the ground state.